In this lesson, we're going to cover integration of rational functions by partial fraction decomposition and rationalizing substitution. If you have two fractions and you're trying to subtract them, first you need a common denominator, and then you'll get your resulting fraction. And then it says we can integrate the rational function by going backwards. So if we wanted to integrate this rational function, we could go backwards and rewrite it as its two original fractions. And then in this form, we can integrate the first fraction minus the integral of the second fraction. You'd pull the 2 to the front, and then the integral of 1 over x minus 1, you could use u substitution and let u equal the denominator. When you take the derivative, you just get 1, and then the integral of 1 over u is ln absolute value of u, and then you plug the u back in. And then you do the same process for this fraction, and you'll get minus ln the absolute value of x plus 2 plus c. In order to go backwards, we're going to use partial fraction decomposition. For rational functions, a rational function is proper if the degree of the numerator is less than the degree of the denominator. If this is the case, then we're going to express a sum of simple fractions using partial fraction decomposition. A rational function is improper if the degree of the numerator is greater than or equal to the degree of the denominator. If this is the case, we'll then use long division and then express it as a sum of simple fractions using partial fraction decomposition. This example says, express the proper rational function as a sum of partial fractions. Do not solve for the constants. So this is going to be a proper rational function because the degree of the numerator is less than the degree of the denominator. Again, the degree of the numerator is going to be 1 because that's the power of this x, and the degree of the denominator is going to be 2 because that's the power down here. So next we're going to express this fraction as a sum of partial fractions. So our first step is going to be to factor the denominator. Since we have two factors, we're going to split it up to two different fractions. We take the first factor and put it in the denominator of the first fraction, and the second factor goes in the denominator of the second fraction. And both of these are linear factors because their degree is both 1. And when you have a linear denominator, then your numerator is going to be just a constant. So first we'll just start with the letter A, that's your constant numerator. This denominator is also linear, so its numerator is also going to be a constant. So we'll just work down the alphabet, so we'll use B. So again, the denominators are linear, therefore the numerators are a constant. So now we've written our rational function as a sum of partial fractions. And again, it said do not solve for the constants, so we're just going to leave our answer like this. For part B, again, this is a proper rational function. The numerator has a degree of 1. And technically in the denominator, because we have this x squared times another x, so the degree in the denominator is 3. So this is also a proper rational function. This denominator is already in factored form. So first I want to look at this factor right here, just x. So we're going to put the factor x in the denominator of one of our fractions. And this is linear, its power is 1, so we're going to start with its constant numerator, which is going to be a. Next, we have this factor right here, x minus 1. When you have a factor that has a power on it, you want to account for all the combinations. So first, we're going to list just x minus 1 to the 1, and then we're going to include x minus 1 quantity squared. So if this said to the third power, we would do x minus 1 to the 1, x minus 1 to the 2, and then also x minus 1 to the 3. You can see this factor is linear, so its numerator is going to be a constant. So going down in the alphabet, we'll use B. This one's kind of funky. It says x minus 1 squared. So what you want to think about it is in factored form, the factor is still linear. So I know technically it represents x minus 1 times x minus 1, which if you FOIL it out, but since the actual factors are linear, you're still going to use a constant numerator. So we'll use the letter C. So here's our final answer, a sum of partial fractions. For part C, we still have a proper rational function. The degree of the numerator is 1 and the degree of the denominator is 3. So again, the degree of the numerator is less than the degree of the denominator. Next, we check the denominator to see if it factors. So we get x times the quantity x squared plus 1. We have two different factors, so we're going to break it up into two fractions. So we're going to take this first factor of x and put it in the denominator. Since this is linear, we're going to have a constant numerator, so we're going to use a. Then we take our other factor and we're going to write that in the next fraction in the denominator. And you'll notice that this denominator is not linear, it's a quadratic. And so that means since it's a quadratic, we're going to have a linear numerator. So when you have a quadratic denominator, it makes a linear numerator. And the way a linear numerator works is you start off with the next letter. So since this is A, we're going to start off with B. But to be linear, it's going to be bx, and then plus, and then we go down in the alphabet, so our constant is going to be c. So I just made a note over here. We have a linear numerator with an irreducible denominator, where you can't factor this anymore, so it's just a quadratic, so that's why you have a linear numerator. This example says if we have this rational function and it breaks up to a over x minus 1 plus bx plus c over x squared plus 2, then if you find a, b, and c and add them together, the answer is going to be which one of these answer choices. So here's the original proper rational function. This factor was linear, so it's written right here with a constant numerator. This is an irreducible quadratic denominator, so it's written over here, and since it's quadratic and it's not factorable, that means the numerator was linear. So it goes down in the alphabet with bx plus c. So again, the rational function has already been written as a sum of partial fractions. So now we're going to finish the partial fraction decomposition process to then solve for a, b, and c. So the first step is you want to think of this like an equation, and we're going to multiply both sides by this denominator. When we multiply this side of the equation by this, the entire denominator will cancel out and we're just left with 3. When we multiply this, we want to distribute to both of these. And when we multiply this expression by this fraction, the x minus 1s are going to cancel, so we're just left with a times the quantity x squared plus 2. Next, when we multiply this to this fraction, this x squared plus 2 cancels with this x squared plus 2. So then we have bx plus c times the quantity x minus 1. So next we distribute the a and then we FOIL this out. Next we're going to take these terms and we're going to group them. So we moved the x squared terms together, we moved the x terms together, and then the constants together. Next we're going to factor out x squared here, and we're going to factor out x. So when you factor out x squared, you're left with a plus b, and I just moved the x squared to the right. Over here we factored out the x, so when you factor an x out, you're left with negative b plus c. And then finally I just put these constants together in a parentheses just to group them. At this point, we're going to set up a system of equations. You can see that on the left side of the equation, all you have is a constant. You do not have an x term and you don't have an x squared term. So since we don't have an x squared term, it's technically 0x squared. And then right here we have a plus b x squared. So we can set a plus b equal to 0. For our x term, we have negative b plus c as the coefficient, and there's no x term over here, so we're going to do the same thing. We're going to set negative b plus c equal to 0. And then finally on this side, we have 2a minus c as the constant, and over here we do have a constant, so we're going to set this constant equal to this constant. So we have 2a minus c equals 3. Since we have 3 equations and 3 variables, the first thing I want to do is combine these top 2 equations. So when we add these 2 equations together, on this side when we add down, the b's are going to cancel and we're left with a plus c. And then over here 0 plus 0 equals 0. So we get a plus c equals 0. Next I'm going to recopy this equation over here. And now we can combine these 2 equations. When we add down, you get 1a plus 2a is 3a, and 0 plus 3 is 3. So we end up getting that a equals 1. Next, I'm going to take this value for a and plug it into the top equation and solve for b. So you end up getting that b is equal to negative 1. And then finally, I'm going to take this a and plug it into the bottom equation to solve for c. So we end up getting that c is equal to negative 1. So a plus b plus c is going to be 1 plus negative 1 plus negative 1, which equals negative 1. So that means our final answer is b, negative 1. This example says evaluate the integral. For part A, we have the integral of x squared over x plus 4 dx. So this is an improper rational function because the degree of the numerator is greater than or equal to the degree of the denominator. So I wrote that over here. When you have an improper rational function, then what you're going to do is you're first going to do long division. So we're going to take x squared and we're going to divide by x plus 4. So we set up our long division and we take the x plus 4 and put it on the outside. Then we take this x squared and we're going to write x squared. And then I'm just going to fill this in plus 0x plus 0. So remember for long division, we're saying what times x makes this first term. So that's going to be x. Once you identify this, you take it and multiply it to both of these terms and you write it down here. So x times x is going to be x squared, and x times 4 is going to be 4x. Next, we're supposed to subtract these, but subtracting is the same as adding the opposite. So I'm going to say plus and then minus, minus. And now you can see that these x squareds are going to cancel. Here you have 0x plus a negative 4x, so that makes negative 4x. And then I'm going to drop down this plus 0. And we're going to do the process over again. We're going to say what times this first term makes this first term. So again, what number times x makes negative 4x? So we get negative 4. Once we identify this, we take it and we multiply it to both of these terms. So we're going to take negative 4 and times by x, and then negative 4 times positive 4. And we're going to write them both down here. And again, instead of subtracting these, we're going to add their opposites. So negative 4x and positive 4x, those cancel. And then 0 plus 16 is going to make 16. And because x doesn't fit into 16, this is going to be our remainder. So by dividing x squared by x plus 4, we're getting the answer x minus 4 plus the remainder of 16. And we take the 16 and we put it over the thing we divided by. So we're going to write all of this out over here. So again, up here is our answer, so we're going to write that out here. And then we're going to add the remainder, and the remainder is 16 over the thing we divided by, which is x plus 4. So using long division, we rewrote this expression as x minus 4 plus 16 over the quantity x plus 4. At this point, we can integrate x and we can integrate negative 4. The integral of x is 1/2 x squared. The integral of negative 4 with respect to x is going to be negative 4x. I'm going to drop down this plus 16. So again, the numerator, I just drop it down. And then you have the integral of 1 over x plus 4. Again, the integral of 1 over x plus 4, it requires u substitution. If you let u equal the denominator, when you write that down over on the side and you take the derivative, you're just going to get 1. So it doesn't generate any new values. And then at that point, you're integrating 1 over u, which is ln absolute value of u. And then you plug the u back in, which is x plus 4. So again, the integral of 1 over x plus 4 is ln absolute value of x plus 4. So here's our final answer. We have 1/2 x squared minus 4x plus 16 times ln of the absolute value of x plus 4 plus c. For this example, we have the integral of 1 over x squared minus 9 dx. This rational function is proper because the degree of the numerator is less than the degree of the denominator. Next, we're going to check the denominator. The denominator factors, and since it factors, we're going to use partial fraction decomposition to rewrite it. So x squared minus 9 factors to x plus 3 times x minus 3. We're going to take both of these linear factors and rewrite them as two separate fractions. Since this denominator is linear, we have a constant numerator. Since this denominator is also linear, we have a constant numerator as well, but we just use a and then b. At this point, we're going to multiply both sides of this equation by this quantity x plus 3 times x minus 3. So this cancels with this denominator and we just have 1. When we take x plus 3 times x minus 3 and we multiply it to this fraction, the x plus 3's cancel, and then we're left with a times x minus 3. Similarly, over here, these x minus 3's cancel and we're just left with b times the quantity x plus 3. Next, we're going to distribute the a and the b. So when you take these two terms, and you write them next to each other and you factor out an x, you get a plus b times x. And then we have this constant, and we're going to write them over here. So we have plus and then negative 3a plus 3b. Since this is an equation, what we're going to do is we're going to look on this side. We don't have an x term. So we're going to take this coefficient of a plus b in front of the x, and we're going to set it equal to 0 because we don't have an x term over here. And then we have this constant expression, which is equal to this constant over here. So we're going to set negative 3a plus 3b equal to 1. So we have a system of two equations and two variables. To solve this, I'm going to multiply this top equation by 3. So we multiply the 3 times a, we get 3a. 3 times b is 3b. And 3 times 0 is 0. Next, we're going to copy this whole equation over. And now we can add down. These terms are going to cancel. We get 6b equals, and we add these together and we get 1. So we end up getting that b equals 1/6, and then we take this 1/6 and we can plug it into either equation. I'm going to plug it in the top one. So a plus 1/6 equals 0. So that means that a is going to equal negative 1/6. So we have our two constant values, a and b. So we're going to take these values, we're going to plug them in right here, and we're going to replace this original rational function with these two new fractions. So again, I took the a value, plugged it in here, took the b value, plugged it in here, and rewrote it like this. So we have negative 1/6 over x plus 3 plus 1/6 over x minus 3, and we still have the integral of this. So a couple of things, these both have a 1/6 in them, so I'm going to pull the 1/6 to the front. So now we're ready to integrate. What we're doing is we're taking the integral of the first fraction plus the integral of the second fraction. Again, technically, we're supposed to let u equal this denominator. If you let u equal x plus 3 and you take the derivative, you're just going to get 1. It doesn't generate any new values. So we can just go ahead and integrate it. If when you let u equal the denominator and you take a derivative, if it generates any numbers other than 1, then you probably want to show all that work just to make sure you don't mess up on any of the coefficients. So when you integrate, because again, when you let u equal the denominators and you take the derivative, you just get 1. Then when you integrate, you get the ln absolute value of u, and then you plug the u back in. So that's why we're getting negative ln of absolute value of x plus 3 plus ln absolute value of x minus 3. So we have the positive ln first, and then the negative natural log over here. So again, just a reminder, when you have minus, you can condense your logarithms to your quotient, so it's x minus 3 on top, and then the x plus 3 on the bottom. So it condenses to just one natural log of this quotient. And then I just dropped the 1/6 and the plus c down. So here's our final answer. This example says the integral from 0 to 1, and we have this rational function. This is a proper rational function. The degree of the numerator is less than the degree of the denominator. And then we check the denominator, and it does factor. So when your denominator factors, then you're going to use partial fraction decomposition to break it down. So we split this up and we do a over x plus 2 and then b over x plus 1. We treat this like an equation, and we're going to times both sides by the quantity x plus 2 times x plus 1. So over here, this will cancel with this denominator, and we're just left with x minus 1. Over here, when we distribute this to both of these fractions, the x plus 2 cancels with this one, so we're left with a times x plus 1. And then when we multiply this expression to this fraction, the x plus 1's cancel, and we're left with b times x plus 2. We're going to distribute the a and distribute the b. We're going to move this ax and bx together, and then factor the x out, and then move these constants together. So when we factor the x out, it's a plus b times the quantity x, and then the a plus 2b is written over here. On the left side, this term right here is x. Its coefficient is a positive 1. And then over here we have x, and its coefficient is the quantity a plus b. So we're going to set 1 equal to a plus b. Next, we have a constant of negative 1, and we're going to set negative 1 equal to the constant over here, which is a plus 2b. So now we have a system of two equations with two variables. So now that we have a and b, we're going to plug them in here and here, and then we're going to rewrite this rational function as the sum of its partial fractions. So we have the integral from 0 to 1, and again, the 3 got plugged in here, so we have 3 over x plus 2. We have negative 2 for b, we plug it in right here, so we get negative 2 over the quantity x plus 1. And now we're ready to integrate. So when we integrate, I'm going to drop the 3 down and drop the negative 2 down. But what we have is 1 over x plus 2, and then we have 1 over x plus 1. Again, technically we're supposed to let u equal the x plus 2, but when you take the derivative, you just get 1. So it doesn't generate any values. If it does generate a value other than 1, then you'll want to write it down to show your work. Since the u equals x plus 2 and the derivative is just 1, we can think of it as the integral of 1 over u is ln absolute value of u, and then we plug the u back in. We dropped the 3 down, we took the integral of 1 over u, and we got ln absolute value of u, plug the u back in, and now we're ready to write the next one. And one more thing, since we plugged the u's back in, we didn't need to convert the limits. So again, you could do this problem totally separate. You could have split these up individually, so you could have done the integral from 0 to 1 of 3 over x plus 2 dx, and then you could have set up a second integral from 0 to 1 of negative 2 over x plus 1, and you could do the whole u substitution and convert your upper and lower limits. That will also work. But again, because the derivative of our u's was just 1, we just quickly took the integral and we plugged our u's back in. And it's really important to note, again, because we plug the u's back in, we don't convert our upper and lower limits. All right, so at this point, we're going to plug in 1 to everything minus plugging in 0 to everything. The natural log of 1 is 0. So we have 3 natural log of 3 minus 2 natural log of 2, and then we have minus 3 natural log of 2. We're going to combine these, and we end up getting negative 5 natural log of 2. Next, we're going to use properties of logs, so we're going to move this 3 up here into the exponent, and this 5 up here into that exponent. So now we get natural log of 27 minus natural log of 32. And then finally, we can condense this. So our final answer is the natural log of 27 divided by 32. Our next definition says rationalizing substitution. It's where you use u substitution, and then you're going to let u equal the radical of the function. This example says to evaluate the integral from 0 to 1 of 1 over 1 plus the cube root of x dx. So by this definition up here, we're going to let u equal the radical expression. So that means for this problem, u is going to be equal to the cube root of x. Next, we're going to take this expression and we're going to isolate the x. And to do so, we're going to cube both sides. So we get u cubed equals x. Now we're going to take the derivative of both sides. The derivative of u cubed is going to be 3u squared. And then I'm going to write du. The derivative of x is 1, but then I'm going to put dx. And then next, we're going to change our upper and lower limits. So we're going to take this 1 and plug it in right here for x. And you just get 1. Then we're going to take 0 and plug it in for x, and you get 0. All right, we're ready to plug all of this in over here. When we converted our upper and lower limits, we still got 1 and 0, so I just rewrote those in. We have 1 over 1 plus, and then this is u. And then for dx, we're going to plug in 3u squared du. So here's our integral. I want to take this 3 and pull it to the front. And then I have this u squared on top, and then I just rewrote this as u plus 1 du. So to integrate this rational function, it's improper, so we're going to use long division. So u squared over u plus 1, so we take the u plus 1 and write it on the outside, and then we take this u squared and put it in here, and then I'm going to write 0u plus 0. To start, we're going to say what times u makes u squared, and we get u. Then we take this u and we distribute it to both of these, and we write it down here. So u times u is u squared, u times 1 is u. At this point, we're going to subtract these, which is the same as adding their opposites. So the u squareds are going to cancel, and then you have 0u plus negative u is going to make negative u. And then we do this again. We say what times u makes negative u. So that's going to be negative 1. Then we take the negative 1 and we multiply it to both of these terms out here and write it down here. So negative 1 times u is negative u, and negative 1 times positive 1 is negative 1. Next, we're going to add their opposites. So the negative u and positive u cancel out, and then 0 plus 1 is going to be 1. So we're going to rewrite this rational function as u minus 1 plus the remainder of 1 divided by the quantity u plus 1. And at this point, we're ready to integrate. I'm going to drop this 3 down. The integral of u is going to be 1/2 u squared. The integral of negative 1 is going to be negative u. And for this part right here, we would do a substitution. We already have the letter u, so I'll use w for example. If we let w equal the denominator, the derivative of the denominator is 1. It doesn't generate any values. So you would just have 1 over w. The integral of 1 over w would be ln absolute value of w, and then you plug the w back in, which is u plus 1. So when we integrate this, we end up getting ln absolute value of u plus 1. And again, because I plugged this back in, we didn't convert our limits. And now we're ready to take 1 and plug it into everything, minus plugging in 0 for everything. So this just makes 1/2. We drop down the negative 1, and then right here we get 2. Absolute value of 2 is just 2. 1/2 take away 1 is negative 1/2. I'm going to distribute this 3 in. So we have negative 3/2 plus 3 ln of 2. And then I'm going to move this 3 up here. So this becomes 2 cubed, which is going to be 8. So here's our final answer, negative 3/2 plus ln of 8. All right, guys, thanks for watching.